Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I'm your host, the Dabbling Doggo.
I dabble.
Last week, we started to learn what makes Julia, Julia. We learned about the magic of methods and multiple dispatch. We learned about composite types and how to create our own custom data types. Finally, we looked at some style guides to help us adopt some best practices as we write our code. Today, we'll add to our coding toolkit by learning how to use the text editor and how to apply some debugging techniques. We'll also learn how to use Julia's package manager and how to install packages. Finally, we'll go through a demonstration of Julia's plotting capabilities by taking a look at some data visualizations. This will wrap up part 1 of this tutorial series. By the end of this tutorial, you will possess all of the basic tools needed to continue onto the next stage of your Julia adventure. Until now, we've been learning Julia by using the REPL. As a reminder, REPL stands for Read, Eval, Print, Loop. The REPL is a great tool for beginners because it provides immediate feedback on our code. Sometimes it produces the result we were expecting, but more importantly, sometimes it produces an error message to let us know that something went wrong. Getting error messages is a great way to learn. However, while the REPL is a great tool for trying out short blocks of code, it's not a practical tool for writing longer programs. Also, there's no way to save your code when you're typing in the REPL. For that, you need a text editor. A text editor is exactly what the name implies. It edits text. A basic example of a text editor is Notepad, which comes included with Windows. You can type in your code into any text editor, but notice that when you hit enter, nothing happens. That's because it's a text editor and not a REPL. While it's possible to create programs using a basic text editor like Notepad, most programmers are looking for something a little more sophisticated. In Atom, click on the top icon along the left side taskbar. Clicking on the icon will generate a new tab next to your REPL called Untitled. Click on line 1 and type in some code. As soon as you started typing, it made suggestions for you. As soon as you typed in an open parenthesis, it automatically created a closing parenthesis. As soon as you typed in an open quote, it automatically created a closing quote. It displayed the code in different colors. When you hit enter, nothing happened. In order to have Julia read your code, evaluate your code, and print a result, simply select the line or lines of code to evaluate, and click on the icon that looks like a lightning rod. This process is called running your code, and the keyboard shortcut is Shift-Enter. So what happened? A checkmark appeared, but it didn't print Hello World. Or did it? Take a look at your REPL. Julia printed Hello World in your REPL. That's great, but it's inconvenient to have to click back and forth between your text document and the REPL. You can move the REPL panel by clicking on the REPL tab and dragging it to some other part of your screen. A lot of developers like to have their text document on top and have the REPL on the bottom, so you can see both at the same time. You can adjust the size of the REPL panel by clicking and dragging the horizontal bar between the panels. Click in the text document and enter a math operation. Again, nothing happened. Select the line and hit Shift-Enter. What happened? Julia printed 2 next to 1 plus 1, but not in the REPL. You can change where you see the result of math operations. Go to File, Settings, Packages, Julia Client. Select Settings. Expand UI Options. Under Result Display Mode, you have 3 options. The default option is to display the result next to the code. Your other option is to display the result under the code, or to display the result in the REPL. Select Display Results under the code and go back to your document. Reselect 1 plus 1 and hit Shift-Enter. Now the result shows up below your code. Go back to the Setting tab and select Display the Results in the REPL. Go back to your text documents reselect 1 plus 1, and hit Shift-Enter. Now the result displays in the REPL. I'm going to go back to using the default setting and having the result displayed next to the code, but feel free to experiment on your own. Let's write a simple function in our text document. Before running this code, let's take a look at it. If you hover your cursor between the line number and the function block, you'll see a couple of down arrows to indicate blocks, or nested blocks of code. Clicking on the arrows will collapse or expand those blocks. Also, the text editor automatically indented your code for you, so you don't have to worry about using the tab key or spaces. In order to run your function, highlight the function block by left-clicking and dragging the line numbers, and then hit Shift-Enter. Notice that my for loop showed up in a couple of places. It showed up next to the code, as expected, but it also showed up in the workspace panel, meaning that it is now available in the global scope. That means anyone using this REPL can use your function. Let's try it out in the REPL. Hopefully, you're beginning to see where this is headed. If you could create a text file with a bunch of useful functions, and if a user could include your file in their Julia session, then potentially anyone in the world could benefit from your functions. In an oversimplified way, this is how Julia works. All of the so-called built-in functions that we've been using are written in a text document and saved as a text file with a .jl file extension. They are actually stored on your computer and were part of the Julia installation process. When you open up a new Julia session in the REPL, Julia is actually loading those files into your active session so that you can use those built-in functions. Let's create a .jl file to see how that works. Before we begin, go to your desktop and create a folder called My Julia Files. In Atom, close your untitled document by clicking on the X in the tab, but do not save it. Create a new untitled document by clicking on the new document icon. Go to Juno, Working Directory, Select. Select Desktop, My Julia Files. Notice that the REPL displays your working directory name. In the untitled document, let's create some functions. Remember that the hashtag sign is used for single-line comments. Now click on the Save icon. Name your file myfunctions.jl. Don't forget the .jl file extension. Close your text document by clicking on the X. Click in your REPL and try to use your functions. Nothing but errors, right? Before you can use your functions, you need to tell Julia to include your files in the global scope by using the include function. Don't forget the quotation marks, and don't forget the .jl file extension. Now look at your workspace panel. All of your functions have been added to the global scope. Use the up arrow to re-enter all of your function calls. Pretty cool, right? The text editor in Atom is not magic. You can actually do the same thing using a generic notepad. In a generic text editor like Notepad, it's better to use 4 spaces rather than the tab key, since Notepad lacks formatting capabilities. Now save the file in the My Julia Files folder and name it notepadtest.jl. Save it as an all files and not as a .txt file. Close Notepad. Click in the REPL and try out your new function. Nothing happened, right? Now tell Julia to include your Notepad function in the global scope. Now try to call your function again. It worked! In theory, you could use any generic text editor to write code in any programming language, not just Julia. However, text editors like Atom offer a lot more features to help you along the way. I am, by no means, an expert on using text editors, since I'm still learning myself. Here's the URL for the Juno documentation for more information. A link is provided in the description below. In the MIT lecture series, there's an entire lecture dedicated to testing, debugging, exceptions, and assertions. In this tutorial, I will only touch on these topics briefly, since most beginners will not be writing lengthy code, and thus will not require a lot of troubleshooting. However, if you are at a more advanced level and find that you could use more tools to help you debug your code, please check out their lecture on the subject. A link is provided in the description below. When writing code, it's important to develop a defensive programming attitude, which will help avoid having bugs in the first place. Here are some things that you can do to avoid bugs. Modularize your program into bite-sized chunks. Reuse chunks of code with functions. Write specifications for functions. Check conditions on inputs and outputs. After you've written your code, you'll want to have it tested and validated before making it available to users. Here are the basic testing classes: unit testing, integration testing, and regression testing. Unit testing validates each piece of the program and tests each function separately. Integration testing is performed after unit testing. The test integrates all units and retests them to ensure that each unit interacts well with each other. Finally, regression testing is performed after all of the changes have been made. The test is rerun to ensure compliance. Here are the basic testing approaches: black box testing, glass box testing, and the modern view. Black box testing explores the paths through specifications. It tests the functionality of the program, and it's performed by someone other than the programmer. The tester is not allowed to view the code, but instead merely tests to see if the output matches the expectations outlined in the specifications. Glass box testing explores the path through the actual code. It tests the internal structure of the code and tests all possible paths for every statement and branch. A modern view is one that embraces the notion that the line between black box testing and glass box testing has blurred and become less relevant. What's important is that you develop a robust testing protocol that tests functionality and non-functionality while removing programmer bias. So far, nothing extraordinary here, simply a lot of common sense advice. When trying to find a bug in your program, you may be so frustrated that you may forget all of this common sense advice. Let's take a look at some debugging techniques that will help you lower your blood pressure. And by debugging, I mean finding and fixing errors in your code manually, rather than using some outside software to automate the process for you. If something goes wrong when running your code, don't be disappointed. Just view it as an opportunity to learn. With that said, here are some tools you can use to debug your program. 1. Check for syntax errors. For example, typos, missing parentheses, missing quotes, etc. These are usually easy to catch, and Julia will most likely give you a syntax error message. 2. Check for semantic errors. For example, the expression does not make any sense, etc. You may or may not get an error message here, so it's important to read through your code carefully to see if what you wrote is what you meant. 3. Use print debugging. Use the println function inside of your functions. Use the println functions inside of your loops. Use the println function to display inputs, outputs, and parameters. Note that the println function within your functions will slow down your programs, so be sure to comment them out with a hashtag once you've debugged your program. 4. Use the scientific method. Step 1. Define a question. Step 2. Gather information and resources. Step 3. Form an exploratory hypothesis. Step 4. Test the hypothesis by performing an experiment and collecting data. Step 5. Analyze the data. Step 6. Interpret the data and draw conclusions. Did that solve your issue? If not, form a new hypothesis, and repeat the process. 5. Draw pictures. If you're a visual learner, you may find it useful to draw out your understanding of the situation. There's something about the act of taking abstract concepts from inside your head and using your hand to visualize it through drawing or doodling that helps bring clarity to otherwise confusing scenarios. 6. Take a break. This may be self-explanatory, but it's amazing how many people fail to do this. There's no point in working 80 hours per week and neglecting to take your vacation days. After some point, your constant work will become unproductive, and you'll be amazed by how clear things will become after you've taken some time away to clear your mind. 7. Use rubber duck debugging. Rubber duck debugging is a real thing. The idea is to describe your issue out loud to an inanimate object. The very act of trying to verbalize your issue may trigger something in your brain to make you realize the root cause of your issue. In case you're wondering, this YouTube channel is my rubber duck debugging project. If you're trying to learn Julia, I highly recommend starting a Julia programming YouTube channel. Even if no one watches your videos, you will greatly benefit from the experience. I realize that I'm no Julia expert, but I've learned a lot just by making these videos, and you can too. If you are watching this video, thank you very much. There are 3 types of errors you may encounter when running a program with a bug: a syntax error, a runtime error, or a logic error. Syntax errors are generally easy to correct. For example, a syntax error may be the result of a typo, missing parenthesis, or missing quotation mark. A runtime error happens when your program contains an illegal operation. The program will stop and an error message is displayed. Logical errors are the most difficult to spot and correct, since you will not receive an error message. You will know you have a logical error when the resulting output is different than a known expectation. Here are some examples of error messages in Julia. Bounds error. You'll see this error if you try to access beyond the limits of an array. Method error. You'll see this error if you try to convert an inappropriate type. Undefined variable error. You'll see this error if you try to reference a non-existing variable. Syntax error. You'll see this error if you forget to close parentheses or quotation marks, or any other typo. Julia provides handlers for exceptions using the try, catch, end block. @warn is a macro that you can use to display a warning message. You can use assertions when you want to be sure that the assumptions on the state of your computation are what you expected. You can use an assert statement to raise an assertion error if the assumptions are not met. @assert is a macro that throws an assertion error if a condition is false. Using assertions is an example of good defensive programming. The subject of testing, debugging, exceptions, and assertions is a very large one. Hopefully, this brief introduction gives you a flavor of the tools that are available as your programs start getting larger and more sophisticated. Another way to add sophistication to your projects is to use packages. In Julia, a package is software that is outside of the base Julia code. Some of the packages were written by the creators of Julia, but most of them were written by individuals or teams who simply have an interest in Julia and want to share their knowledge with the Julia community. As of this recording in the fall of 2020, there are over 4,500 registered Julia packages. That number is a little misleading since anyone is allowed to register a Julia package and not all registered packages are actively maintained. However, with that said, there are still a lot of Julia packages. There is no way to review all of these packages in this tutorial, so instead, I'll show you how to add packages to your local environment, and I'll give you a demonstration of a few packages so you can get a feel for how to use them. There are two ways to add a package to your environment. One, you can add a package directly from the REPL, or two, you can use Julia's built-in package manager. Let's add a couple of packages, one from the REPL and one using the package manager. To add a package from the REPL, use pkg.add followed by parentheses and quotes. Place the package name within the quotes and hit enter. OhmyREPL is the name of the package, and be sure to follow the camel case since package names are case sensitive. Once complete, enter the close bracket to enter the package manager. This environment is called the package REPL. It displays in a different color so it's not confused with the primary Julia REPL. To display all of your options within the package REPL, simply type in the question mark and hit enter. To see a list of all of your installed packages, type in status. To add a package from the package REPL, simply type in add without the pkg, followed by the package name, without parentheses and without quotation marks. To exit the package REPL and return to the Julia REPL, simply use the backspace key. Before you can use your newly installed packages, you need to call them by using the keyword using, followed by the name of the package, without parentheses and without quotation marks. This is required for every new Julia session. Although these packages were downloaded onto your computer, Julia will not assume that you want to use them for every Julia session. Let's try typing in some code. Your code now displays in different colors, thanks to the OhmyREPL package, which has transformed your REPL into something that looks like a fancy text editor. Maybe it's useful, maybe it's not. Either way, it's a fun example of how an outside package can enhance your Julia experience. The package benchmark tools added a macro called @benchmark, which provides a sophisticated tool to measure the performance of your programs. Let's take a look at a couple of examples. Notice that the @benchmark macro doesn't print the results of your function, only the performance data. NS is the abbreviation for nanoseconds, which is 1 second divided by 1 billion, or 1 billionth of a second. The @benchmark macro runs your function multiple times and records the length of time for each run. If you lined up all the runs in order, from lowest value to the highest value, the median value is the value in the middle. The mean value is the weighted average of all of the runs. In other words, if you added all of the individual times together and then divided by the number of runs, that's the mean value. That notation you see for the time is for microseconds, which is 1 second divided by 1 million, or 1 millionth of a second. The first letter is the lowercase Greek letter mu. In order to get to nanoseconds, slide the decimal point over to the right by 3 places. If you look at the mean time, or average time, it's over 100 times slower to generate an addition table that's 50 by 50 versus one that's 5 by 5. Recall that the function addTable has a nested loop, which becomes increasingly less efficient as the number of loops get larger. Now, it's over 10,000 times slower. We'll discuss program efficiency later in this tutorial series, but this is a good introduction to understand why programming efficiency is important. There are some packages that come included with Julia, so there's no need to add them. However, you still need to call them before you can use them. Let's take a look at 3 packages included with Julia: random, statistics, and linear algebra. We've used the rand function before, but there's a whole world of random number functions available in the random package. The rand function uses a uniform distribution when generating random numbers. The randn function uses a normal distribution when generating numbers, meaning that over a large sample size, the average value will be 0, and the data will have a standard deviation of 1, meaning that most of the data will fall somewhere between -1 and 1. You can also generate random strings using the randString function. This can come in handy if you need a random password generator. You can use the shuffle function to randomly shuffle your collection of data. You can use the underscore if you're not using the iterator for any calculations. This is only a temporary shuffle. You can permanently shuffle the collection by using the shuffle bang function. Now the change is permanent. In the past, we've calculated averages by taking the sum of a collection of numbers and dividing by the length of the collection. Why doesn't Julia have a built-in function for average? Well, it does. The function is called mean, and it's part of the statistics package. We just saw median being used in the benchmark tools package. As a reminder, the median is the value right in the middle of a sorted collection of data. The standard deviation is a measure of how widely the data collection is spread out. Knowledge of statistics is not required for my tutorials, but these are some commonly used statistics functions that are good to know. I'm not sure how many of you have taken a linear algebra class, or if you have, how many of you remember linear algebra. Linear algebra is not a requirement for my tutorials, but linear algebra is used a lot in computing. Here's an example of how easy it is to solve linear algebra problems using computing. Let's use the following example. ax plus by equals c, dx plus ey equals f. A, b, c, d, e, and f are known constants. X and y are unknown variables. Find the values of x and y that solve both equations. Back when I was in school, we learned linear algebra the old-fashioned way before computers. Back in the olden days, we used graph paper and drew lines on a graph. We solved these equations by looking at the intersection of the lines. The x and y coordinates at the intersection was the solution to the problem. Now, let's see how it's done using computing. Let's use random numbers for a, b, d, and e, which are the constants on the left-hand side of the equations. Let's use random numbers for c and f, which are the constants on the right-hand side of the equations. In order to find the x and y, all you need to do is use the backslash operator. Let's check the math to see if that worked. They're the same, so that worked. They're the same too, so that worked as well. Easy, right? Much better than using graph paper. We could spend all day going through the different packages, but it would be more fun for you to explore them on your own. Here are some resources to help you discover more packages for you to play with. Julia Hub is a website operated by Julia Computing, which is a for-profit consulting firm founded by the creators of the Julia programming language. Julia Observer is a website that provides some great resources if you're looking to explore some new Julia packages. Links are provided in the description below. Before we begin the next session, close out of Atom and relaunch Atom and Julia. Some of the most commonly used packages in Julia are the plotting packages. Plotting is a great way to help you visualize your data and to share that information with others. Before I learned to code, I used the term plots and graphs interchangeably. However, in computing, the term graph has a very specific meaning. In computing, graph refers to a form of data visualization using vertices and edges, or nodes and lines. It's often used to represent networks of communication. It has become increasingly popular in this age of social media to show social connections. Graph theory is a separate subject on its own, so I will not be covering these graphs. I will be covering your standard line charts, scatter plots, bar charts, etc. In computing, these are called plots. Plotting is an enormous subject and can fill an entire tutorial series. Therefore, I will not be covering everything associated with plotting in this tutorial. Instead, I will be providing an introduction to plotting in Julia, along with some demonstrations of its capabilities. If plotting is a subject that interests you, I will be covering this subject in more detail in my next tutorial series that will begin in early 2021, so stay tuned for that. There are several different plotting packages available for Julia. For today's demonstration, I will be using a plotting package called Maki.jl. It's a relatively new plotting package, but it's showing enormous potential, so it's a good one to know. Install Maki like any other package. It's a very large package, so it may take a while. After that's complete, you can call the Maki package like any other package. For starters, let's try creating a simple line plot. In Maki, you generate a line plot using a function called lines. In Maki, plots are called scenes. You can zoom in and out by clicking on the plot and using the scroll wheel on your mouse. Scroll away from you, and the plot gets smaller. Scroll towards you, and the plot gets bigger. You can pan from side to side and up and down by right-clicking and dragging the plot. What you're seeing are the default values for a plot in Maki. If you don't like the black color, you can change it. In order to use a different line color, you can include color as a keyword argument in the lines function. Notice that the color is of type symbol. You can see a list of the available named colors in the colors.jl documentation. As you can see, there are a lot of named colors to choose from. Maybe the line is too thin for you, and you want to increase the thickness. For that, you can add line width as a keyword argument to the lines function. You can save your scene to your computer. Go to the REPL and use the save function. Enter a file name in quotes as the first argument. Make sure that your file name has a .png file extension. Then, enter the variable name scene as your first argument, separated by a comma. Look in your My Julia Files folder on your desktop and double-click on your PNG image. Easy, right? Let's take a look at a few more examples. In this example, Maki is using the range from -10 to 10 for the x-coordinates and using f of x equals x squared to calculate the y-coordinates. Let's take a look at a few scatter plots. Let's start by setting up some arrays filled with some random values. You can create a scatter plot by using the scatter function instead of using the lines function. Also, you can control the size of the marker by using the keyword argument marker size. This generated a scatter plot using 1 to 100 as the x-coordinates and using the array y for the y-coordinates. This generated a scatter plot using the array x for the x-coordinates and using the array y for the y-coordinates. So you can see that all of the values on both the x-axis and the y-axis fall between 0 and 1. This is a three-dimensional plot. You can pan from side to side and up and down by right-clicking and dragging with your mouse, just like you could with a two-dimensional plot. However, when zooming in and out, the scroll wheel direction has flipped for some reason. To zoom in, scroll the wheel away from you. To zoom out, scroll the wheel towards you. You can also orbit around the plot by left-clicking and dragging with your mouse. It takes a little practice, but it's extremely useful. The control is a bit sensitive, so move your mouse slowly for the best results. You can add to an existing plot by using the bang operator. Here's how you generate a bar plot. Here's how you generate a heat map plot. Okay, so that was simple enough. Now, how do we add titles and labels to our plot? Here's how to add axis labels to an existing scene. The syntax here is unusual, so it'll take some time to get used to. However, this syntax offers a glimpse into how Maki works under the hood. Here's how to add a title to an existing scene. You can't actually mutate a scene with a title, so you need to assign it to a new variable name, which is why I'm using the variable name SceneWithTitle. You can save your image like before. This plot looks okay, but it's not really presentation ready. It's more of a functional tool for experiments. There's another package called Maki Layout that offers a lot more options for presentation quality layouts. However, it's still under development and it's a little too complicated for a beginner course. Again, if this is an area that interests you, be on the lookout for my next tutorial series starting in January 2021, where I will cover data visualization in more detail. For now, this should give you an idea of what's out there regarding plotting in Julia. For more information on plotting using the Maki package, please refer to the official Maki documentation. Well, that's it for now. Today, we learned how to use the text editor and about some debugging techniques. Then, we learned how to use Julia's package manager and how to add packages. Finally, we were introduced to the world of plotting using the Maki package. Believe it or not, this concludes part 1 of this tutorial series. If you made it this far, congratulations! In just 8 tutorials, you now possess the basic knowledge and tools to advance to the next level. Next week, we'll begin diving deeper into programming by learning about algorithms and recursion. If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. New tutorials are posted on Sundays. If you have any questions, please post them in the comments below. Feel free to spread the word by sharing this video, since I'm sure you'll all agree that this is the finest tutorial on all of YouTube.
Worst tutorial ever.